Hi there, and welcome to my regular physics lesson on work and energy. It's snowing outside, so I figured I'd wear the hat I got in Scotland. It just makes me feel a little bit warm and cozy. So let's have at it and do a little learning here. So the topic is going to be work and energy, and so let's go ahead and see what these things are. So what is work? So basically, there's a relationship between these two things that we'll discuss. So something that has energy has the ability to do work. So something that does work is changing the energy of an object. So the relationship from an algebraic standpoint is that work, which we'll represent with a capital W, is equal to the change, and of course remember that this means change, in energy. And specifically we're going to say kinetic energy. So I'm going to express kinetic energy with Ke, and I'm going to represent potential energy with Pe. Sometimes you'll see it represented just with a capital K, or this one with a capital U. However, I am going to stay consistent with my textbooks and represent it like this. So each one of these two things has their own equation, and we'll get into that. There is different types of potential energy, and I'll express those as well. So work, however, work equal to the change in kinetic energy. What is work? So let's focus on what work is first. Let me make a little bit of space for that. So work is, in its most basic form, equal to force times distance. Now what's important about that is that the force and the distance are parallel to each other. So oftentimes we'll have a little symbol here that is not a number 11, that is rather just to mean that these two things must be parallel to each other. So the force must be parallel to the distance, or really displacement. And so let's look at an example of that scenario. So if we have, let's say, an object, okay, that is on some sort of flat level surface. Okay, let's see if it'll let me move this relative to each other. There we go. So it's on a flat level surface, and let's say that this flat level surface is friction free. Then when we push this object, we are doing work to cause it to accelerate or decelerate or anything like that. Okay, so let's go ahead and apply a force. So let's apply a force onto this object, okay, into this direction. And we're going to cause this object to accelerate because, again, this is friction free. So yes, the force is equal to ma, right? So that force is equal to ma, as it always is. But that's not really what I want to focus on so much. Instead, I want to express that that force times the distance, right? The force times the distance is equal to the work done. Okay, and I'm going to express this relationship, which, by the way, is known as the work-energy theorem. So it's the work, okay, I'll just go ahead and write it out. It is the work-energy theorem. And so is work always done whenever there is a force? And I will say no. What if you apply a force straight up? However, that force is not large enough to overcome the force of, let's say, gravity. So if you apply a force up, and you have a force of gravity acting down, you'll notice that the force acting up is not as big as the force of gravity. And of course, you also have a normal force that is acting up in order to keep this thing from not accelerating. So are you doing work? No, because it's not being displaced. Okay, the object is not accelerating. It's not moving at all whatsoever. You are doing no work onto the system. What if the object is in fact moving? What if it is moving left and right and you are pulling up on it? Are you doing work then? So let's say that the box, for example, is sliding from our left to our right on some sort of friction-free surface. It is already in motion, it continues to be in motion. And as it's doing that, you pull up trying to lift it, but you're unable to. You're pulling up, you are applying a force. It is moving left to right. So there is a displacement, there is a force, is there work? And the answer is no, because there is no part of this force that is in the same direction as the displacement. So let's shift it so that way there's something in between. Let's make this force at some angle. Of course, we can break this force down into its vector components, so let's go ahead and do that. So let's break it down into its x and its y components. So now let's look at what work is being done. So let's again say that this box is in fact sliding from the left to the right. It's not being lifted up, okay? There's a part of the force that is in the up direction, but it's not actually accelerating up. It's not even off the ground. So is there work being done onto this object? There could be friction, there could not be friction. I would assume that if there's not friction, that it is in fact accelerating from left to right, because there is this part of the force that is causing it to accelerate in that x direction, in that lateral direction. And so is there work being done? I would say yes, because there is at least a component, right? There is a component of the force that is parallel to the displacement. The displacement is left to right. So what you would do is you would figure out how much of the force is in this direction, and you would apply that force, right? You can pretty much ignore this, and you can take this force and apply it. You can apply it to the displacement and say, okay, if I know that it's moving from some given distance, okay, it's moving from here off over to here, that's the distance that it's moved, and you apply a force during that time, and your force is going to be this much in that direction, right? You're actually applying a force up at an angle, but it's this much of your force that is actually going towards accelerating it or moving it. And so multiply those two things together and you would get the work done. Now what if there is friction? Are you still doing work? Does it have to be accelerating for work to be done? So let's say that there is some sort of surface here, right? Some sort of surface that has friction to it. So I'm just going to color that in to represent a surface that does in fact have friction. And so let's say in that case, you are just getting it to maintain its velocity. So it's already in motion, and you're going to go ahead and just apply a force right in this upward and to the right direction. We're going to apply a force, just getting it to kind of maintain its velocity. Are you doing work? Well, are you applying a force that is in a direction parallel to the displacement? Yes, you are. And say, yes, you are in fact doing work. Then where is that energy going? It's going into heating up the object. And so this work equals change in kinetic energy. That's a little bit, can be a little bit of an issue, but we're going to go ahead and say that work is still being done. It is just that it's being taken away from that kinetic energy and going into thermal energy. So let's look a little bit more specifically at what kinetic energy is. So we have an equation for that. Let's go ahead and express what that is. So kinetic energy is equal to 1/2 mv squared. Okay, 1/2 mv squared. So the mass of the object times its velocity in meters per second squared. So if we have an object that is moving at some given velocity, okay, so we're going to make an object anytime now. We're going to make an object, and we're going to have a velocity a velocity v off in that direction, and we can determine what its kinetic energy is by taking 1/2 mv squared. What I want you to recognize is something very important, that if you initially had this object at some velocity v, and then you double that velocity, so let's make it twice as big of a velocity, so it's going to be now a value of 2v, okay? How have you changed the kinetic energy? Since you doubled the velocity, is the kinetic energy going to be also doubled? And the answer to that is no. It will be not doubled. It will be different than that. So let's take a look. Let's take this equation, let's rewrite it over here. So the kinetic energy is equal to 1/2 mv squared. And I purposely left a little bit of space in there. I'm going to put parentheses around the v. The reason being is because I'm changing the v, so I want to make my change to it first, then apply the other parts of the equation. So I'm going to double it. Okay, so let's go ahead and double the velocity. when you double the velocity, this square gets applied to the 2, and it also gets applied to the v. So this turns into 1/2 m, it gets applied as 2 squared v squared. And so if I change the right side of the equation, I have to also change the left side of the equation. So how much did I change the right side of the equation by? Well, instead of it being 1/2 mv squared, it's now 1/2 m. Well, what's 2 squared? 2 squared is the same thing as 4. Okay, so let's go ahead and change that to a 4, right? 2 squared is the same thing as 4, so I'm going to change that. So the right side of the equation is, instead of it being 1/2 mv squared, it's now 1/2 times 4 v squared. So that means that the right side of the equation has changed by a factor of 4. So I must change the left side of the equation by a factor of 4 to keep the two sides equal. So that means that the kinetic energy has increased by 4 times. So if I were to double my velocity, the kinetic energy of the object is now 4 times greater. And that's a very important thing to think about as we move on. So please consider that. Please keep that in mind. All right, so let's move on to potential energy for a moment. Okay, what is potential energy? So potential energy is at least gravitational. I'm going to put a little g there. Gravitational potential energy is equal to mgh or mgy. They're the same thing. It's the change in height or the change in the y position of the object. And so this is measured in meters. This is the acceleration of gravity, and of course the mass of the object. So what this means is that if you have some sort of object, let me go ahead and erase this stuff for a moment. If you have some sort of object that you have at some given height off of the ground, right? So we generally will consider to be the height of the ground to be your 0 position, right? So that's 0 meters, and here I have my object. And so when you take your object and you drop it, there we go. And so we're going to drop it. It's going to start at this height over here, and it falls. And what's happening to its potential energy? Its potential energy is clearly decreasing, right? If I have a large height, then it's going to have a lot of potential energy. And why does it have potential energy? Well, because as I let go of it, it's going to pick up speed, and then pick up more speed, and pick up more speed. So it has the potential of converting into another type of energy, specifically kinetic energy in this case. So here's what happens. We have something known as the law of conservation of energy. The law of conservation of energy. And this is a very important idea, okay? Very, very important idea. So it basically says that energy cannot be created nor destroyed. Okay, I went ahead and wrote that in. So energy cannot be created nor destroyed. So essentially, however much energy total, right? Not just kinetic energy, not just potential energy, but all of your energies together. Whatever energy you have at position 1, you will also have that much energy at position 2. If you don't, you have to account for where it went to, because it went somewhere. It didn't just disappear. And so that's the law of conservation of energy, which is a very important law. So we can express that algebraically like this. We can say that the kinetic energy at position 1 plus the potential energy at position 1 equals the kinetic energy at position 2 plus the potential energy at position 2. And this is a pretty typical way to express this. So what we're going to say, let me go ahead and move this off to the right. And so we're going to say that at position 1, so let's go ahead and label this as positions 1 and 2. So this is going to be position 1 up here, and down here is position 2. And so when it starts at position 1, it has, let's just say that it's an object that you're just like holding there and it's at rest and you're about to let go of it. So that's at position 1 or at phase 1 or at time 1. And so you're about to let go of it, so let's evaluate what its kinetic and potential energies are. Well, it's at rest. so that means that its kinetic energy is 0. So we can go ahead and take that out. But the rest of it, I'm going to go ahead and copy down the equations associated with it. Okay, I could go ahead and write that out. In fact, let's go ahead and write it. So we have 1/2 mv squared, and I have a feeling that my big fat hat wearing head is going to be in the way, so let me move this up just a little bit. Okay, so we have 1/2 mv squared, right? That's the velocity at position 1 specifically, plus the mgy or mgh, either one, and this is the position. This is at position 1, and that's going to equal the kinetic energy at position 2. Okay, so let's write the 1/2 mv squared at position 2 plus the potential energy at position 2. Okay, so that's going to be mgy, but that's the position for position 2. Okay, so let's go ahead and look at these things. So at position 1, as we said, the kinetic energy is 0, right? Since its velocity is 0, this whole thing, let me switch colors back to red. So this whole thing, this is 0, so that means that this whole part right here is 0. I'm going to go ahead and scratch it out. Okay. And is anything else 0? Well, is the potential energy at position 1 0? No, because it has all of this height to it, and that's definitely got potential energy. What about at position 2? So when it hits the ground, does it have kinetic energy? And this is where sometimes people get confused. Sometimes people will say no, because it hits the ground and it comes to a stop. No, we are not concerned about that. The part of it hitting the ground is a whole nother event that we will look at. That's a momentum collision. That is something that we will look at separately. Okay, we want to look at the moment just before, right? If you can see my eyes through it, that's the moment just before it hits the ground, and that's what we want to look at. So does it have kinetic energy at position 2? Absolutely. And then what about potential energy? Well, it's at position 0, so this number right here is 0, so that means that this whole thing is 0. And so I'm trying to give you a nice, simple example that we can use to kind of work through some problems. And in fact, another thing is if you notice, it's the same object, it's the same mass, so therefore mass will cancel out in this particular case as well. So let's go ahead and determine what would the velocity at position 2 be. How fast will it be going when it hits the ground? So what we have is basically just gy equals 1/2 v squared. Okay, so let's multiply each side by 2. So I'm going to move over a little bit so my head's not in the way. And so that means that 2 gy, that's the y at position 1, that is equal to, let's see, it gets rid of the 1/2, right? I multiply this side by 2, so it's 2 gy. Multiply this side by 2, it gets rid of the 1/2. So that's going to be equal to v squared, specifically the velocity at position 2. And then lastly, I take the square root. So that means the velocity at position 2 is equal to the square root of 2 gy. Okay, and that's it. So if you have, let's say for example you have a 1 meter high distance that you're going to drop something from. So it will that'll be 1 times, let's say about 10 meters per second squared acceleration and gravity. So 1 times 10 is 10, and then times 2, and so you've got 20, and then take the square root of that, and so then that will give you the velocity. So the square root of 20 looks to be about 4.47, and so that's how fast it would be moving, 4.47 meters per second. If you were to drop it from a height of 1 meter, that's how fast it'll hit the ground. And this is, of course, something we can have solved with regular kinematics, but this applies like this as well. What if we have some sort of like curved ramp that is friction-free? We put a block on this ramp, so that way this block will go down the ramp and slide down it. How fast will the block be going when it gets down here? It'll be moving in this direction, but you know what? Since the change in height, since the change in height is the same 1 meter, then the math works out to be exactly the same actually. And so with kinematics, you can't really go through that logic, but with energy, you can say it has potential energy here, it has kinetic energy here, and there was no energy lost to heat due to the friction. Okay, so that is the use of the conservation of energy. And so I think what I'd like to do is to probably go ahead and do an example of the work energy theorem. So let me take a moment for that. Now, I had already expressed to you that when you increase or double your velocity, your kinetic energy is also doubled. And here's where that's going to come into play. So as we said, the work is equal to the change in energy. So work is equal to the change in kinetic energy. Now, since work is equal to force times distance, and kinetic energy is equal to 1/2 mv squared, basically, force times distance equals 1/2 m delta v squared, where the v is the thing that is going to change. And here's what I'd like to look at. Again, just like before, I would like to express to you a certain example. We have a car. I'm going to really poorly draw a car, and this car is going to be moving along in that direction, and it's going to come to a complete stop. So it's going to slam on the brakes and then come to a complete stop. So if that car was going, let's say, 20 miles per hour. So at 20 miles per hour, the tires are going to have some sort of friction force acting on them in order to come to a stop, and that friction force would actually be about the same regardless if you're going 20 miles per hour, 25, 30, 40, 50, 60. For the most part, the friction force, as long as you are just completely slamming on the brakes, the friction force will for the most part be about the same in all of those scenarios. And so that friction force is consistent. What isn't consistent is your stopping distance. How long does it take you to come to a stop? So if you were to be moving at 20 miles per hour in the school zone, it would give you some amount of distance to come to a stop. Now let's compare how that would change if you were now moving instead of 20 miles per hour, instead now you're going 40 miles per hour. So you should recognize that you are going twice as fast. So you've increased your velocity, you have doubled it. Let me go ahead and get rid of some of this stuff. So you have now doubled, right? Put parentheses around this. You have doubled your velocity. And as we said before, that's going to change the other side of the equation by a factor of 4 because it's 2 squared. Force doesn't change. Your stopping distance does. So I want you to recognize this. If you're in the school zone and you were to instead go 20 miles per hour, instead you go to 40 miles per hour, your stopping distance is now 4 times more than what it was before. And most people do not understand that. Please, and I am being very serious, please take that into consideration. When you go a little bit faster, your stopping distance is a lot farther. It is an exponential increase in stopping distance, which is why the school zones are such a slow speed. It is crucially important. Little Billy is going to appreciate it when he runs out into the street for his ball and you are able to stop in time. So physics is around you every single day. I want you to please appreciate it as best as you can, and I want you to learn more of it so you understand how to apply it in everyday life. So here's my general intro on work and energy, and I hope that we are able to learn more about it. So with that, I will see you guys next time. You guys have a great one. Take care.